All right, so today we're going to be talking about baghouses, what they are, what they're used for, and how you as an environmental engineer or environmental consultant can prepare your baghouse emission estimates for submitting your notice of intent, your Title V operating permit application, or in just adding that new technology, that new installation at your facility or updating your old equipment. So first of all, just going through a baghouse, as you can tell from this picture, baghouses can range in size. Some are very large, such as this one, and some are very small. Baghouses are used to capture particulate matter in your process stream or in the air and remove it so that you can decontaminate your process stream. Particulate matter, such as PM10 and PM2.5, are criteria air pollutants as recognized by the EPA. And so it's critical that we consider the effective removal of these pollutants in our roles as engineers. So we've developed this template for projecting baghouse emission calculations, as well as comparing some of the costs of this type of equipment to some other equipment such as cyclones and ESPs. As a brief and general introduction, AQ Analyst provides this template. Just as a disclaimer, it is protected under copyright laws and not to be used for duplication. If you have any questions though and you want to prepare a document, we're happy to help you. Just reach out in the comments on this video below or ask for help and we'd be happy to assist you in any of your needs. So with that, we also like to acknowledge the EPA, AWMA, and NDEP for the publicly available resources that they have published that have allowed us to create this document to assist you. So with that, let's go on to baghouses. There are three different types of baghouses that are primarily used in industry. The first is a pulse jet baghouse, followed by mechanical shakers and reverse air. According to the EPA, it doesn't really matter which one you use. They look at the achievable emission reduction as about equivalent between all three of them. However, pulse jet is a little bit more effective than the other two, but they all operate around the same operating temperature and they all face the same problems. Now, what I mean by that is, as you can tell, they're very high control efficiencies and emission removal efficiencies when operated properly. However, they have huge problems when you're dealing with material that is corrosive, extremely high temperature, or with a high moisture content. Anything that is moist or wet can generally cause clogging in the baghouses. If you're a concrete batch plant, for example, you need to consider this when you are applying water to your stockpiles and then using a baghouse to control the conveyor belts that carry the concrete material. Reason being is if these baghouses get clogged and your permit states that these baghouses will operate to control conveyors, then you cannot continue with your plant operations with those conveyors until your baghouses are back and operational. So it's really important to make sure that these things are running properly, and so you need to consider the application of them. With that, baghouses are generally used for mineral processing and grain milling, as well as different types of boilers, whether that's industrial or commercial or even sometimes residential. There are other types of emission control devices for particulate matter, such as cyclones, electrostatic precipitators, both wet or dry, and Venturi scrubbers. As you can tell, these different control devices have similar emission reductions that are achieved, 70 to 90% or 90 to 99, where baghouses are 95 to 99. So they're in the same ballpark. As you can tell in column G and column F, the average annualized cost for these baghouses vary and cyclones vary differently. And quite frankly, baghouses aren't the cheapest option. So why would we consider using them? If you look at it, cyclones are much cheaper, right? The maximum general cost in dollars per standard cubic foot per minute is $13.5. That's fairly cheap compared with your pulse jet baghouse that can be as high as $39 per standard cubic feet per minute. So why would we use them? The main answer is if we have to achieve BACT, or best achievable control technologies. Now, if your facility is subject to BACT, you have to prove that the technology you're using is the best one available when considering cost, effectiveness, and a few other factors. Now, as you can tell, these baghouses are close enough in cost. They are higher, but if you look at $1 per ton pollutant removed, they're close enough that often EPA or your local Department of Air Quality will require you to use a baghouse as part of BACT. So that's why we would use them, unless they're not technically feasible, right, such as high moisture content. In which case you may consider something else, such as a Venturi scrubber or wet electrostatic precipitator. These are these other options that have various flexibility. You can also tell with cyclones, they can operate at very high temperatures, up to 1,000 degrees, or dry ESPs up to 1,300 degrees. With that, with the general view of the control devices, let's look at baghouse calculations. So here we just prepared a small template for general inputs. Everything highlighted in yellow we can update. So in this scenario, we've assumed that there are 4 different baghouses with their various flow rates, again in standard cubic feet per minute. We assume that these baghouses will operate 24 hours a day and the whole year, so 8,760 hours per year. Now, there are different ways to calculate baghouse emissions. You can calculate it on a pound per ton basis if you're moving aggregate material or just solid material that you can measure. You can calculate on a pound per hour basis, depending on what governing authority has given you that guideline. Or the alternative measure is to provide an outlet grain loading rate, which is effectively a guaranteed emission standard or emission rate that you have agreed as an engineer, saying this baghouse will never emit more than this grain loading. Typically, that grain loading rate is 0.005 or 0.01 grains per dry standard cubic foot. So that is the standard. It varies a little bit from industry. 0.005 is a little bit harder to maintain. And so you may want to consider going for 0.01 if you can. The reason I like going off of this option is if you are working at, say, Nestle, and you're making pasta, and you're making hundreds of thousands of these different single meal packets a day, and you have a baghouse that's controlling the dust from adding in a bunch of flour or yeast or what have you into your food. If you have it regulated on a pound per ton basis, then when a change in your industry happens and there's a huge demand for more pasta, you're not legally allowed to increase your throughput because you've been limited on your permit to a specific pound per ton. Your emissions have been specified as a total, say, 200 tons per year, or more realistically, say 5 tons per year for your baghouse. Well, if you all of a sudden have double the demand for homemade bread, then your emissions are going to increase. They're going to double because you're going to double the use of your flour, which means you're going to double the use of your you're going to double the throughput. So I don't recommend doing that because if you get it baked into your permit, it can take several months to be able to adapt to the market conditions that are constantly changing. However, if you calculate your emissions on a grain per DCFF basis, you may have to submit standardized stack testing to show that your baghouses are constantly in compliance. So it's a give and take. You have to compare constantly. But with that, we've got this scenario set up, and let's go through the emission calculations. So for our 4 baghouses, we're going to get them on a pound per hour basis, a pound per day basis, and a ton per year basis. Now, just with the brief scenario that we've set up, You can see that the total tons per year for these baghouses, not very large. It's just 7 tons per year. But that's because of the different sizes of baghouses we have used and the outlet grain loading. The largest baghouse we've assumed is 10,000. That can vary distinctly depending on what facility and operations you're working with. So if you're a cement plant, for example, you could have a baghouse that's sized as high as 50,000 CFM. An example of this we pulled up online. This is public information. We just pulled from the Utah permit search. So if we go through here, there's a client that has been using 3 different baghouses to control process streams for their asphalt mixing drum. And as you notice, the baghouse needs to be sized. Their single asphalt plant baghouse has to be sized to handle 57,000 ACFM for their conditions. Now, if we go back to our emission estimate, 57,000, it's going to change our emissions from 7 tons per year to 24. So it is a big jump. But again, it is industry specific. So you can update all of those according to your size. But going on our emission calculations, we start with the grain per dry standard cubic foot outlet grain loading rate. With that rate, we're going to convert into a pound per hour basis. From pounds per hour, we're going to convert to both pounds per day and tons per year. The reason we get these 3 different values is if you are required to perform modeling for your permit application, you need to show that your grams per second rate is not exceeding the applicable threshold. You also need to show that the pounds per day, your maximum pounds per day, are not exceeding your threshold as well. And on a ton per year basis, you need to know where you stand in terms of, are you a major source or a minor source when we factor in all your different emission sources. So what we do is we take the grain per dry standard cubic foot per minute, the grain per DCFF, and we're going to multiply that by, or we're going to convert that into pounds. So we're going to multiply that by 7,000 grains per pound. We're also going to multiply that by the flow rate of our baghouse. So if that's 2,500 standard cubic feet per minute, for example. And then from there, we're going to convert our minutes into hours. And then we're just going to multiply by our baghouse quantity. So for example, we only have one baghouse, number 1, and we have converted from grains to pounds. We've converted from, we've multiplied that by the SCFM, and we convert that from a per minute basis to an hourly basis, and now we have pounds per hour. From the pounds per hour, we're going to multiply that by our maximum operating hours per day to get our daily emissions, as you can tell here. And then we're going to multiply our hourly emissions by our annual operating hours per year to get our annual emissions. And then we're going to divide it by 2,000 to convert from pounds to tons. Now, as you can tell, it's a fairly simple process, and all of this you can Google. Honestly, it's public knowledge, it's public information. And so here in the footnotes below, we've also just presented the general calculation methodology below. If you're an environmental engineer, it's very useful for the agency that's reviewing your document to be able to see your work and the equations that you used. It's very effective as well if you're trying to spot check any errors that you've made. So that's the simple way to calculate baghouse emissions. From there, we just sum it up using a simple calculation, and we can see our total hourly emission, our total daily emission, and our total annual emissions. Now, as you can tell, this is assuming 8,760 hours per year of operation, which is continuous. Obviously, that's not realistic for most industries. Generally, there is some downtime. The reason that we do this is, first and foremost, you're calculating potential to emit emissions, or PTE. On a PTE basis, we need to assume that everything is running to the maximum that you would want it to run for a year. Now, realistically, you could say that your potential to emit, your maximum potential, is 90% because you have, plant shut down for a few weeks out of the year or something of that manner. But with this, the reason that I like to have the 8,760 is that you need to keep in mind that the way that you calculate your emissions is the way that you are going to be subject to limitations. So for, again, going back to the emission factor, if you did a pound per ton basis, then you are limited to the throughput for X amount of tons per year. It doesn't matter if market conditions change and you need to double your throughput to make money. It's not going to happen legally until you change your permit. But if we base it on this outlet grain loading, and if we base it on the maximum operating hours in a year, then we can change our operations. We can add more. If we normally work, let's say 6,000 hours per year, well, we've already got a permit to run for 8,760. And so it's okay legally to increase our operating conditions because we still have not hit our maximum potential as prepared by our PTE. Now, all of that is obviously subject to state limitations and source specific. So you may have actual emissions that are also regulated, but in most states, you just have to make sure that your PTE is not exceeded and that you are compliant with that. So that's how we calculate our baghouse emissions. Just to review again, baghouses have very high control efficiencies. They're managed to filter out particulate matter from different process operations such as milling and mineral processing. There are other types of equipment we could use, some that are much cheaper such as cyclones, and that will depend on your process. With baghouses, we just take the flow rate and the operating hours per year and we multiply that by an outlet grain loading rate, and then use our simple dimensional analysis to convert into hourly, daily, and annual emissions. Now, there are other methods to do this calculation. If you wanted to do source-specific emission factors, such as that, you can do that. For example, from AP 42, Chapter 11, you can pull up the conveyor emission factor, and you can use the controlled emission factor because baghouses are controlling that conveyor. I wouldn't recommend that because baghouses are much more effective and efficient, and so you'll present your emissions as much higher if you use the controlled emission factors as opposed to using the baghouse control emission factor. You can also use a throughput-based emission factor. That, again, as we mentioned, restricts your operational flexibility. And the source-specific one, if we'll be honest, that's going to be painstaking, as you'll have to find the specific emission factor for all your conveyors, any loading drums, etc., your different bins of material that you need to account for. You can also use region-specific emission factors as required. For example, some regions such as the South Coast Air Quality Management District may require you to use a different conveyor emission factor than EPA does. So obviously adhere to whatever agency you're trying to get your permit approved through so that you can operate and so that you can make your plant more efficient and more productive. This wraps up our video. We have more videos such as how to project bulldozing emission calculations as well. And we have many more videos to come. So if you have any questions, please leave us a comment below or visit our site. That's AQ Analysts. We're happy to help you if you have any questions. Thanks.